Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 16 in your Unit 4 homework. So let's see, we've got this system here which is released from rest. And if we think about what's going to happen, assuming that our pin is working fairly well and stuff like that, this object is going to start accelerating down. So if I kind of, do my motion diagram, dot, 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 right? And then this thing is going to start to accelerate this way, rotationally. Now, we have a choice as to how to work this problem. Typically, these things boil down to either Newton's second law or principles of work and energy. And either one will work here. But if we look at the numbers that are given here, we know that this thing starts off the floor 2 meters. This is stated in the problem. And we can hopefully observe, right, here's my symbol for observe here, that the potential energy of that object is going down. Meanwhile, its kinetic energy is going up, and the kinetic energy of this object is also going up. So this is just set up very nicely for a work energy theorem type of problem. So remember, in the work energy theorem, you draw the system at state 1. So here's this object at state 1 is here, and it's not moving. State 2, this object is down here, and it's moving. It's important to realize, though, a little bit of daylight there. We want state 2 to be before it hits the ground. Okay. Then write out your work energy theorem, right? Potential energy 1 plus kinetic energy 1 plus work from 1 to 2 equals potential energy 2 plus kinetic energy 2. I would put your datum at the floor. That would be a good place to put it. All right. Now your PE1. This thing right here obviously has a PE1. Hopefully that's obvious. Equal to mgh. This thing, the disk, has a potential energy, but notice that it's not changing. So even if we do put something for PE1, we're going to have the same something for PE2. And those somethings just divide out, or subtract off, I'm sorry. So long story short, the pulley is not changing potential energy. You don't need to worry about it. Okay? KE1, well, it says system is released. I guess I didn't actually say from rest, but it was intended to be from rest. Okay? We'll talk about that work term here in a moment. I always do those last. Okay, potential energy 2, right? This object is at the floor. Okay. Kinetic energy 2. This object is moving, so it will have a kinetic energy, a 1/2 mv squared term, right? But you're going to put that under the KE2. However, this disk is also rotating, so it has a kinetic energy of 1/2 I omega squared, right? That's the kinetic energy of a rotating body. Right? So that too needs to go under the KE2 term. Okay, now, the I, like what do we do about that? All right, this is a disk geometry, 40 centimeters in radius. So I gave you a handout on a bunch of geometries here. I'll let you look this up. Look up how to calculate the moment of inertia of a disk. Okay. Then the other thing you're going to have to take into account, what do we do about this thing? So remember, again, from the definition of a radian. Right, the radian is all about like a slice of pizza, and the crust is called your arc length, right? And then you have a radius, and then this is an angle theta, or let me call it a change in theta. And from the idea of a radian, your change in theta is equal to the ratio of S over R, this divided by this. That's what a radian is. And this equation normally is written S equals R times theta, or this time I'm going to write it change in theta. And when you divide by time, specifically delta t, really, you're dividing by a change in time, right? Distance over time becomes a speed. And change in theta over change in time, that's what we call our angular velocity. That's what this is. Change in theta over change in time. Or in the language of calculus, it's d theta dt. That's not important to realize for this problem. So when you have your work energy theorem, you can either put this in for here, and then you would solve for the angular speed. Or, right, you can take this and write the angular speed as v over r, and you can sub that here, and then solve the resulting equation for v. And again, when I say here, I'm talking about under, in this KE2 term. So hopefully that will get you through part A of this problem. I'll talk a little bit about part B here. How many seconds did this take? So that is a question about motion. Oops, trying to figure out how to scroll back. Oh, okay, I won't bother scrolling back. That object started up high, accelerated down, and if we did a quick sketch of velocity against time, as we usually do, at the top of its motion, its velocity is 0. At the bottom of the motion, its velocity is some number that you now have from part A. For this graph, I would just do down positive, and that's going to make this graph look like this. And we don't know the t, but you do know this. That's the velocity at position 2 that you calculated earlier. And the distance that this object traveled is going to equal this area right here. That should be enough to get you through t. So I hope that this helps. Have a great day.